Okay, away you go.
Cool. Thank you. Thank you very much, Joanna. Hi, everyone. My name is Javier Almansa Sobrino. I'm part of the OSS team at ARM. I've been working at ARM for the past 2 years and a half, almost 3 years now. First, I started as working on the TFA project, and then I moved to RMM. And today I'm going to be presenting the interface between RMM and EL3 firmware or TFA. So, yep, starting. So yeah, this is the agenda that I'm going to go through today. So I'm going to start talking a bit about the requirements that RMM will have, a bit about the boot process of RMM and how EL3 firmware is involved on that. Then I will follow up talking about the error handling during the boot phase and the possible return values that RMM can report back to EL3 firmware. Then I will be talking about versioning for the EL3 interface and the boot manifest interface as well. I will then talk about the boot manifest, which is a data structure that we will use to pass platform data between EL3 and RMM. Then I will go a bit into how RMM and EL3 how the runtime calls work between RMM and EL3. Then I will talk a bit about the shared buffer management during EL3 and RMM calls. So I will show that we have a shared memory area between EL3 firmware and RMM that allow us to pass large chunks of data. Then I will discuss the RMM and EL3 word switch register convention. And finally, we have the runtime services, although this is something optional. I'm not going to talk much about that. And finally, I will just show some implementation details on TFA, because here, when I talk about EL3 firmware, I'm not talking about TFA necessarily. So one of the things that we want to do with RMM is that it will be firmware agnostic. It doesn't know what is underneath it. So every time that we talk here about EL3 firmware, we're not talking about TFA, we're talking about a generic firmware. So in the last section of this presentation, I'm going to talk a bit about how we have implemented a few things on TFA. So starting with the requirements, RMM needs to be as platform independent as possible. We want to decouple RMM from the EL3 firmware. So for that, we need that RMM supports a position independent execution. It also needs to be able to receive configuration parameters during boot time. This is because RMM has a minimal set of platform parameters that we can set up during build time, and the rest of the parameters have to be discovered by EL3 firmware and sent to RMM. Also, RMM doesn't depend on any stage prior to BL31, and its configuration is completely independent of the configuration mechanisms used on the EL3 firmware. That will allow any partners to use their own BL2 and BL1 image and any configuration mechanisms they want to use. They can use device trees, they can use fconf, they can use hard-coded parameters. In our case, BL31 will only need to parse and extract the relevant information for RMM and then pass that information, handle that information to RMM during the boot phase. So as mentioned before, RMM will be EL3 firmware agnostic. So when possible, we cannot make any assumption about the what is running underneath RMM. Because of that, we need to have some sort of contract between EL3 and RMM that will tell us how the former will pass information to the latter, how EL3 firmware is going to pass the information to RMM. So some of this information can be, for instance, the number of CPUs that the system has, the address range for certain peripherals, for example, the UART, and the information regarding the shared memory buffer, which I will discuss later. That information will be passed from can be passed from EL3 to RMM via a register contract, as I mentioned before, or via a boot manifest. Actually, for the current implementation, we use both approaches. We pass very few, very limited information through registers from one image to another, and for more platform data, then we use a boot manifest. Also, RMM might require services from EL3 firmware. For instance, RMM may need to get attestation keys, or may need to delegate or undelegate memory granules, etc. So for that, we need to define a set of runtime commands that EL3 must be able to serve to RMM. And for this, we need a formal specification of those services. This is also included on the spec, and I'm going to discuss this a bit as well. Also, this specification defines the switch register convention between RMM and EL3, which is part of the SMCCC contract, when the non-secure world is the client. And yeah, I will also go into more detail about this later. And finally, we also have to manage compatibility between EL3 and RMM, because the EL3 and RMM can evolve in the future, and so because of that, we need to provide some sort of version control on the RMM-EL3 interface. This will allow us to check if given RMM image is compatible with given EL3 firmware. So the only part that is a version here is just the contract between RMM and EL3, which can be different from the version of RMM. So we can have a RMM version X, which a specific version of the boot interface, and then RMM version Y can have the same version of the boot interface and communications interface. Okay, so I wonder if anyone has any question with regard to the requirements. Okay, if not, I will move forward to the boot process. So the boot process is actually relatively simple. So it is always initiated by the root world, in this case by EL3 firmware. So what happened is that EL3 firmware initializes itself, and then it jumps into RMM by performing a context switch. So during that handover to the realm world, RMM will read any boot information that we have passed through registers, will read any information that we have passed through the boot manifest, and then we will perform any initialization that it needs. Once it has initialized, it will return back to EL3, so EL3 can carry on with the rest of initialization. Between the time RMM has initialized itself, or at least has processed the boot parameters, and the time it returns back to EL3, we cater for the possibility that there can be some back and forth communication between RMM and EL3 firmware, in case, for instance, RMM needs to get attestation keys from EL3 and so on. So that is optional and can or cannot happen. But this will always happen after RMM has been processed all the boot information and have some minimal initialization. So as mentioned before, RMM accepts up to 4 arguments. Those are stored in registers X0 to X3. So for the boot interface version 0.1, the register usage is as follows. So for the cool boot path, X0 will contain the linear index for the current P. So this index will start from 0 and must be less than platform core count, which, as you know, is the parameter that we have on TFA to determine the maximum numbers of CPUs supported by the system. So X1 will contain the RMM-EL3 interface version that for this particular specification will be 0.1. X2 will contain the maximum number of CPUs that the system supports. And X3 will contain the base physical address for a shared buffer between EL3 and RMM. So a couple of notes here is that when the system is booting up, what RMM does is to compares the platform core count, the argument passed on X2, it compares with the maximum number of CPUs supported by RMM, which is defined at build time. If the value on X2 is larger, is bigger than the maximum number of CPUs supported by RMM, then the boot will fail. And also the maximum, as mentioned before, X0, the current CPU ID always has to be lower than the platform core count. Finally, on the physical address, we passed on X3. So that's a shared area between RMM and EL3 that can be used later during runtime to pass information. However, during the boot process, it can also contain a boot manifest, which is a data structure where EL3 firmware can store any other platform data needed for RMM to boot up. During the warm boot path, we already have all the information that we need. The only bit of information that is missing is the linear ID for the current CPU. So this is passed on X0, and we don't need any other information for the warm boot. Any questions?
Hey, Varun here. A couple of questions.
Hello.
I missed the start, the initial part of the meeting, so apologies if you have to repeat anything.
Yes.
But in the boot sequence slide, or the
here?
boot process slide here, just want to clarify.
Yeah.
So the RMM in the sequence, you are just zooming into the RMM boot sequence. Does it mean that RMM will boot first in all these worlds? My assumption is secure world will boot before RMM, right? For example.
Yeah, it can boot before RMM. It can boot after RMM. So secure world is not needed for RMM. So it will depend on the EL3 firmware. If EL3 firmware boots secure world first, or if decide to boot RAM world. So something that I explained at the beginning is that this presentation doesn't focus specifically on TFA. It aims to be generic because RMM doesn't make any assumption on which firmware is running. So the presentation is quite generic in the sense that we don't make assumption. We don't consider when I say EL3 firmware, I don't necessarily mean TFA, right? So yeah, depending on how do you implement your EL3 firmware, you can decide to put up secure world or RAM world first. The point here is that the RAM world doesn't need the secure world and vice versa.
Right. Okay. So the policy basically lies in the root and how they want to take care of the boot sequence. Okay, that's fair. On the next slide.
Yes.
So we are passing the. I just want to understand how RMM will use the linear index. I mean, by passing the linear index, are we assuming that RMM and the root will follow the same policy for calculating the linear index? It's possible that root might have a different calculation formula to come up with its own linear indexes. RMM might have a different formula. So are we creating a dependency by passing this in X0?
Yeah, that's actually a very good question. Yeah, we didn't think about that. I think that the assumption that we make here, and that's actually a very good point. I think I should add that to the documentation, is that we assume that the EL3 firmware has a linear ID that runs from 0 all the way up to the maximum number of CPUs supported by the system. So yeah, thank you very much for that point. I will write it down to add this to the specification.
So just to add more color, Usually, to calculate linear index from a given MP-IDR, it requires a platform-specific hash function implemented in RMM. So we want to avoid the dependency on platform-specific parts in RMM. So since EL3 is bound to calculate a linear index, it can pass down that same index to RMM. There is no strict rule that the same ID should be used between EL3 and RMM. As long as RMM gets a unique ID for every PE, and it's between 0 and platform core count, RMM is fine with that.
Right, but isn't there a dependency now? Because RMM depends on root to calculate these index. I mean, RMM
Yes.
might.
Yeah, there is.
Maybe.
That's a dependency. That's part of the RMM-EL3 spec. It's a dependency being placed on EL3. That as part of entering RMM, you have to provide a sequential linear index that is unique for this PE. That's a dependency we are placing on EL3. Yes.
Is it linear index only used for stack calculations, address?
Mostly it is for allocating all the per CPU resources, like per CPU stack, per CPU data structures, any per CPU calculations that we need to perform. Yeah, so it's for that mainly.
It also means that in the cold boot, we can have linear index for the master, for the primary CPU not being 0. Is it correct?
It is possible. It is correct.
Yes.
There's no mandate that the cold boot CPU has to be 0. Yeah.
Okay, and another question to Javier. So when we build RMM, we specify a number of PEs supported. So what's the relationship between platform core count and this number of CPUs? Should platform core count be less than the number of CPUs supported?
Yes, platform core count must be less or same as the maximum number of CPUs supported by RMM during build time. So
Okay.
the relationship here is that we compare platform core count with the maximum number of CPUs supported by RMM build time, and then we compare the linear index of the current CPU with platform core count.
And RMM code currently checks this dependency, so it checks that platform core count is less or equal of the number of CPUs supported.
Yeah.
Sorry, Alexei, can you repeat your question?
So is there a code that actually checks that the platform core count is less or equal of number of CPUs supported? Is there a check for this part of?
Yeah, that is implemented as part of RMM.
I think it would be good to have the note saying that we need to check this parameter as well.
Okay, yeah, thank you. So actually the specification documentation, the documentation for this spec, which is on under review on trustedfirmware.org, it contains more detail. So here I just saw a snapshot, but the spec documentation contains more details.
Okay, thank you.
But anyway, I will add a note there in case it is missed.
Thank you.
Okay, so then we'll carry on talking about the error handling and return values. So after the cold or warm boot has happened, RMM will return back to ELC to EL3 firmware, sorry, by issuing an SMC RMM boot complete call. This call will indicate that the boot has complete, and it will only support one argument, which is on X1 register, which corresponds to the error code. So if there were an error on RMM during boot up in any of the PEs during cold or warm boot, what will happen is that RMM will stop executing immediately, will return back to EL3 firmware, and reporting the error. And then what will happen is that EL3 firmware will treat RMM as not existing. So any SMC that needs to be routed back to EL3 will be treated as unknown SMC. And if RMM was able to boot up on any other APE before this PE failed, it will be disabled for those PEs. They will also won't try to boot up on any remaining PEs. This is just to allow us to present a symmetric view of the RMM into the interface system. So if RMM fails, even in one of the PEs, it will be disabled completely in the whole system. So this is a list of all the possible errors that can happen during the boot up. So we have the first is boot successful, and then apart from an unknown error, which is a generic error, we have errors, for instance, for version mismatching with the boot interface or with the boot manifest, invalid pointer to the set area, CPU ID higher than the maximum reported by RMM by EL3. Sorry, that's an error. CPU maximum number of CPUs larger than the maximum number of CPUs supported by RMM, etc. Okay. I don't know if there's any question on this regard. Okay. So next part is versioning. This is actually very simple. So the EL3 and RMM interface is versioned in order to facilitate the compatibility between versions, between EL3 firmware and RMM. So the version number is passed through X register X1 during cool boot, and is 32 bits wide with bit 31 set as reserved 0. So the version is composed of two fields. We have the version major, which goes from bits 16 to 30. This value is increased if and only if the changes that we make to the boot interface ABI break compatibility with previous versions, which means that we also have to update EL3 firmware. Version minor goes from bits 0 to 15. This value is increased if and only if the changes that we make to the boot interface ABI do not break backwards compatibility with previous versions, or it is reset to 0 if the version major is updated. And finally, we have the res 0 field that we have this field just for consistency with other modules on RMM that also use versioning. So in order to be consistent with all those components, such as the RMI, ABI, and so on, we kept this bit reset as 0. Finally, the boot. Sorry. Yes.
Do we? So do you envision having some OEM versioning fields as well for the RMM?
No, we haven't.
Subversioning fields, rather.
No, we haven't thought of that. Something that we have is that I will explain this later. The boot manifest caters for some platform manifest data. So an OEM could add their own data structure there and then version that data structure if they want. But actually, this data structure, this versioning is for the interface between EL3 and RMM that it is not supposed to have any change regardless of the OEM or anything like that. So an OEM will add platform changes, and then this will be versioned somewhere else.
So this is kind of my issue. So we say platform, we really mean silicon, right? So RMM is tied to silicon. It's not tied to platform. It's going to be silicon specific, not platform specific. So the model where you guys have manifest to describe platform specific information doesn't scale well to an RMM design, right? We have to have only silicon specific information, right? And I know the term platform is used loosely here, but there's a lot of yeah. So I just maybe when we get into the manifest, the type of manifest data that you're talking about.
Yeah, maybe then we can discuss more
Sure,
deeply.
sure.
Yeah.
We can move. Yeah, but on the versioning side, you could envision needing to have silicon specific considerations with respect to RMM. So it'd be, if it's in the manifest, then that's fine, right? But we probably want to talk about like the nature of how you guys envision the manifest to be. If it's a statically compiled thing, like we have today, where you know, then the manifest may not be appropriate. Whereas if the manifest is something that's dynamically created based on discovery of like the silicon, the RTL that you're running on, whatever it might be, and we dynamically populate fields of the manifest, and it's a different story, because there's some things that have to happen based on you know, discovery. Anyways, I'll hold my thoughts until we kind of see what you guys have in mind for the manifest.
Okay. Yep.
So just to, since we are on that topic, I think the current implementation, reference implementation on FPP is dynamic. It's detecting various platform aspects from various sources of information. And that source could be either static or another configuration file. That depends on the platform or the OEM or the silicon. But the manifest itself is constructed dynamically.
The manifest, say that one more time. So I lost the last part. The manifest itself is constructed in what?
It's constructed dynamically in BL3.1 by BL3.1. Yeah, at boot time.
Okay, it's not just loaded from the FIP. It's actually constructed dynamically by BL3.1 in this model.
The data structure is static in the sense that the fields on that data structure are static, but then it is populated by EL3 firmware as it discovers the platform parameters.
Okay, thank you.
Okay,
that sounds good.
Cool. So yeah, let's talk about the boot manifest details now. So as we were just discussing before, so the boot manifest is actually a data structure where we will store platform data. So this data structure will be common to all platforms or silicons in this case. It is mandatory that the platform manifest has the first field as the version number, right? So the version number uses for the platform for the boot manifest, it uses the same format as I explained before for the whole RMM-EL3 interface. And then for this specific version of the platform manifest, we only have a version number, and then we have a pointer that can point to to some platform data. So any partner can add their own data structure to the boot manifest and add any information specific to the platform. So this boot manifest is stored inside the allocated RMM-EL3 shared buffer, and because the current implementation at the moment is only allocates one page of memory, the boot manifest cannot grow larger than one page of memory.
So that's going to be a problem for large scale systems, right?
Well, it can be a problem for a large scale system, yes. But usually the manifest, the thing, what we've thought about this is that the boot manifest data would be the same for all the PEs on the system. So we shouldn't have much per CPU information on this platform data. Bear in mind that the platform, the boot manifest is only passed once during cold boot, and the rest of the PEs, they don't pass any boot manifest at all. They just pass the CPU ID.
No, understood. I think just the point is, right, if you look at the core count on certain systems, we have to describe core topology in the manifest for the SPMC today, right? And once you have a high core count, there's the core count, and then the RMM also has to have IO awareness, and there's a bunch of information that when you have a high IO count as well, you run into similar situations. So I expect if we're doing, go ahead.
So sorry. I was going to mention that at the moment, and I will talk about this later. So we only allocate one page of memory for of one page of shared memory for the whole system, and I will go on the reasons for this later. But actually, if it will be needed to allocate more memory for a larger system, then we should be able to easily do that. So if in the future we need to pass a larger manifest, or we need to increase the amount of shared memory between RMM and EL3, it shouldn't be very problematic. Sorry, you were going to say?
That sounds good.
Yeah. So another thing to keep in mind is in NUMOR V1, RMM or the realm world does not have any IO other than UART for putting out debug logs. So it's only mainly the memory that needs to be defined, described, and some other aspects related to memory. But when device assignment comes in, probably that's when you might have we might have a larger manifest to describe various device properties and aspects like that, and we can certainly bump up the shared memory area, and we can do the necessary over there.
So maybe I'm making too many assumptions here. I'm assuming that this manifest is going to be pretty similar to what we see in an SPMC manifest today.
Yes.
So the core topology would have to be there too, no?
We don't rely on core topology. The RMM doesn't need the organization of the PE in a affinity level scenario. All it needs is core count, the linear index of this PE. It doesn't need to have awareness of the actual topology in the system.
So for like the JIC driver, don't you need to know how to index into like how for interrupt handling and things of that nature, right? You need to know how to index into the JIC-R space. You need MPIDR for SGIs.
Yeah, so all interrupts
I thought that's all in context of NUMOR V1, right?
Yeah, all interrupts will be handled by non-secure. RMM will just hand over control back to non-secure kernel hypervisor, and RMM will not deal with GIC directly. Any interrupt will cause realm world to preempt and go back to the non-secure host. That's how it's designed today.
Okay, so NUMOR until NUMOR V2, your expectation is that core topology. I mean, eventually, once we have, direct IO and direct interrupt support, we're going to have the core topology. Agreed.
So currently, it's not needed for V1. Yeah, that's what we think. Yeah.
Okay, so this includes timer interrupts as well and SGIs. I thought SGIs was still in scope for NUMOR V1. Is the SGIs? How did the SGIs work?
So RMM by itself does not send any SGIs. If the realms want to send an SGI, it might use the GIC virtual CPU interface to poke it, but RMM by itself will not try to program an SGI or deal with SGI details.
Okay, but every time we receive an SGI, we're going to exit the realm.
Yeah.
Every time we receive it, we're going to exit the realm all the way to the hypervisor.
Yes.
And the hypervisor is going to reschedule the realm every single time.
Yeah.
Okay. All right. Yeah. No, that's helpful. I think so it becomes more of a problem with NUMOR V2. But yeah, I think for now it sounds like you're saying only thing is memory and I guess RMM capabilities and attributes.
Yeah.
Is what you expect in the manifest.
Okay, so shall we move forward? So next part is to explain a bit how the RMM and EL3, how the runtime calls work between RMM and EL3. So we have basically two type of RMM EL3 runtime calls. So one, the first ones are when RMM initiates the call. So RMM always sees EL3 as a service provider. So all the calls will always be initiated by RMM. So in this case, it's just a normal flow as can happen, for instance, on the secure world or on the normal world. So RMM just issues an SMC call to the root world. EL3 firmware process that, and once they have the results, it just goes back to EL2 with whatever results it has to report on the registers according to the SMC calling convention. There's not much to explain here. Then we have the scenario in which the normal world wants to make a request to the RMM. So in this case, the normal world cannot make the request directly to RMM. So instead, it needs to use EL3 firmware as a conduit. So what will happen in this case is that the normal world will make the request to EL3 firmware, and then EL3 firmware will forward that call to RMM. RMM will process the call, return back to EL3 firmware with the return value, and then EL3 firmware will return back that value to the normal world. It can happen, for instance, that in between the moment in which RMM receives the call from the root world, and the moment in which it finishes the call and send it back to the normal world, RMM may need to have a number of calls between to EL3 firmware to request for services. For instance, one case can be when we delegate or undelegate a memory granule. The normal world will be the one requesting to delegate a memory granule that is forwarded through EL3 to RMM. RMM receives the petition to delegate a memory granule. It does some housekeeping internally to keep track of which memory is delegated and not, and then it make a request to EL3 firmware to actually delegate that granule. The root firmware is the one who has to delegate, and once it has delegated memory, it goes back to RMM with the result, whether that worked or not, and then RMM calls EL3 firmware again with the answer of the original petition that then is forwarded back to the normal world. The step 3 and 4 are usually optional. Not all the calls between normal world and RMM involve intermediate communication, but between RMM and EL3 firmware, but it's something that can happen. Any questions? Okay, so moving then forward to how the share buffer is managed during RMM and EL3 calls. So the share buffer, one of the main reasons for having a share buffer is to be used during EL3 and RMM communications when we need to pass large data structures. For instance, there are calls, RMM calls that request for platform token or keys, and this data doesn't fit into the registers. So because RMM sees EL3 as a service provider, only RMM can initiate any communication with EL3. That means that if a share buffer, if the share buffer is needed for the communication between RMM and EL3, it is RMM responsibility to lock and own the shared area to avoid any race conditions or to avoid any classes. So when EL3 needs to use the shared buffer, it can safely assume that the PE that make the service call has exclusive access to the shell buffer, and that there's not going to be any classes. Once RMM has finished processing the call, it can release the unlock buffer. It can unlock the shell buffer, and then any other PE that need access to that shell buffer can use it. So I mentioned before that we only have one page of shared memory to be used by all the CPUs. So the rationale behind that, is that initially we thought of using a page of memory per CPU, but we thought that we don't need to use a very extensive use of that shared area, because it's only used at the moment for a couple of system calls, and then the chances of having a class of having some contention due to the shared area was going to be very small. So in order to save memory, we decided to use only one page of memory. However, as I mentioned before, if in the future we need more memory because we need to pass larger data structures, or there are more contention because we make more use of that shared buffer, then it shouldn't be very difficult to just allocate more memory and allow RMM to use larger shared areas.
This buffer is per core?
No, that buffer
Okay.
is for the whole system. It's a
So how do you-
single buffer for all the cores.
So you're gonna serialize.
Yes.
Sorry, I'm gonna ask a lot of questions about scalability because historically we've had a lot of challenges with TFA on a scalability, on a large scale side. If you have a single buffer here, that means every RMM to EL3 call is gonna have to be serialized across all cores.
No, because actually not all the calls need to use the share buffer. The share buffer is only used for calls that need to pass large data structures, such as calls to request a platform token or attestation keys. So those are at the moment we anticipated that the buffer is not going to be heavily used, so it's not going to cause a lot of contention. That's the reason why we decide to use only one page of memory, to be shared across all the PEs. If in the future we see that actually this is a bottleneck and cause contention, then we'll probably move to. It should be easy to move to a scheme in which we have more pages, or larger buffers, or even one page per CPU. But at the moment, we considered that wasn't necessary. That wasn't going to be a bottleneck, and we will save more memory.
So just to add more color, so the only situation where this buffer currently used is during cold boot to retrieve the remote attest platform token from the hardware enhanced security model, the HES module. So really, this buffer is only getting used during cold boot time, and it's never used during runtime. The actual non-secure to RMM doesn't use this buffer. Non-secure will pass a page directly, and RMM can directly access it. This is only for the EL3 services that RMM needs to use. And currently, there is only 2 or 3 services, and they are only invoked during cold boot. They are not used during runtime.
So for attestation services, it sounds like you're assuming that we're gonna have a static copy of the attestation report in the RMM, right? But we have dynamic. Things are changing, potentially changing in the system. So my expectation is whenever we launch a realm, we'd want a fresh attestation report, right?
Yes. So there are details over here. So I think what is retrieved from the HES is only the platform token, which is going to be constant throughout the lifetime of the system, or for a given particular version of firmware. And then what we retrieve is a key. It's not the actual report that is retrieved, it's only the key. And then whenever a realm requests an attestation report, we use this key and we use the information provided by the realm, and also combine the platform attestation token and a couple of other information to create the attestation report dynamically, and that doesn't involve communication between RMM and EL3.
Okay, what does it involve? You're envisioning RMM and HES for that?
RMM and HES. The HES provides the key and the platform attestation token. Yeah.
So like a okay. Yeah. I'm just thinking that, you know, things like debug state of the system can change. There's different you know, maybe I'm thinking forward again to Numore v2 where we have you know, attestation of IO devices which could have been hot plugged in.
Yes.
The attestation report has to be fresh when it so I guess maybe in the future, if you guys have a session on the attestation flows, it'd be interesting to see if there's more RMM to EL3 calls. If you think it's a one cold boot call, I think we're fine with one buffer. But if we see more RMM to EL3 communication where we need to, you know, extract payloads through EL3, whether it's directly or indirectly to the HES, whatever it might be. Yeah, we just want to make sure that we don't get in a situation where you have workloads where you're launching realms, short-lived realms, killing the realms, and every time you launch and kill it, it's, you know, you're doing attestation on a regular basis and you're not creating any. Okay.
Yeah. That can be taken care. Yeah.
Okay, so this
a question around the locking mechanism. So can you help me understand if this is only happening once or twice during cold boot, then what would be the need for the lock?
The need for the lock was to cater for the situation in which we needed to add more calls that need the buffer. So we wanted to make the management of the buffer generic. So we didn't want to make any assumption at the beginning. So in the case in the future we need to add a call that needs that buffer, we already had the infrastructure there.
Okay, and then the locking mechanism, is it a software construct or are you envisioning using IP for the locking?
It's just it's done by software. It's just a normal spin lock that keeps the calling process awaiting until the shell buffer is free. I'm actually what I was going to explain on this slide here. Right, so this slide here, for instance, shows the case of the setup platform token call on RMM. So during boot up or during any other time in which we need to get the platform token, what RMM does is just to get and lock the shared buffer. When called that to get unlock shared area, it will be blocked. It will block the shared buffer until it's not needed anymore. Then the call will just copy any public data information or any information that needs to be passed to EL3. In this case, setup platform token needs to copy the public hash value to the buffer. Then once we have this, the setup platform token will perform an SMC call to invoke the EL3 service. On that SMC call, we can pass a pointer to the physical address to EL3. We will pass a pointer to the physical address of this shared buffer. Then EL3 firmware will do any manipulation that needs to do on that data, on the data on that buffer. In this case, we'll process the public hash value and will copy the platform token into the shared area. Then return the SMC call and setup platform token will do any further processing that need to do on the data that is stored on the shared buffer, and then we'll unlock the shared area and carry on. So the flow here is quite straightforward. We just lock the buffer when we need to use it. RMM blocks the buffer when we need to perform any operation on it, unlock it once it is done. And EL3 never has to worry about the buffer at all, because it knows that it assumes that that buffer is already locked and owned by the calling P. Any more questions? Okay, then moving forward. Next step is the RMM-EL3 World Switch Register Convention. So EL3 is expected to maintain a register context specific to each world, and it will save and restore the registers appropriately as it switches between worlds. So EL3 must maintain a separate register context for all the general purpose registers, as well as a stack pointer on EL0 and EL2. It also needs to maintain the separate register context for all the EL2 system register for all the features that has been enabled by EL3, including any register with the underscore EL2 prefix. And it also needs to keep a register context for EL2 physical and virtual time registers. Sorry, the EL2 physical and virtual time register must not be included on this register context, because those are handled by non-secure world. And finally, EL3 will not save some of the registers, such as the FP and SIM register, SVE, SME, and EL1 and EL0 registers. I don't know if that any question regarding this. Okay. So the next is the runtime services, but this actually I added here as informative. I'm not going to go through this. On the patches that we are reviewing on TFA, this is documented more thoroughly. So this is just to mention that we have so far, there are 4 runtime services. One is to delegate memory granule, to undelegate memory granule, to retrieve the realm attestation key from EL3, and to retrieve the platform token from EL3. But yeah, as I mentioned, that was here just as informative. They will be thoroughly documented on TFA once the patch is merged. And just to finish, as I mentioned before, all these details were weren't specific to TFA, were mostly general. So now I have a couple of slides here to talk a little bit about how we have implemented a few things on TFA. So for the TFA, the boot process is quite similar to how SPM works. So we have STD-SBC service, which is just called RMM-D setup. And then when we call our RMM-D setup, the prerequisite is that we need to have the shared memory area already allocated and properly mapped. Then RMM-D, which is the module on TFA that takes care of bringing up RMM, it will just generate a boot manifest. This is similarly done as how it is on SPM. And then we'll set up the boot parameters on the registers X0 to X3, and then it will just perform a setup context. After that is done, BR31 will initialize RMM by calling RMM init, and then that will perform the first entry to the realm world. RMM will just read the boot parameters, will read the boot manifest and so on, perform an initialization. And once that's done, it will do a context switch back to RMM-D, which will just return to BL31, and the boot process will carry on. Actually, on TFA, RMM is enabled, is initialized after SPM has been initialized, but there's no dependency on that. RMM doesn't need SPM for anything. With regards the shared buffer, so as mentioned before, at the moment, the implementation that we have for FBP is just a single page of memory. This is allocated right below the realm, the area that we have reset for the realm. The realm area and the shared area buffer are mapped as a single GPT block. They share the same attributes. They are mapped as paths, as realm paths, and both areas can be accessed by the realm world as well as from the root world. So BL31 only needs to access to the shared area. BL31 doesn't need to access to the ROM area. The ROM area is only accessed by BL2 during image load. Yeah, BL31 only needs to access to the shared area. Finally, the life cycle, the sub buffer area must be available for the whole life cycle.
Can you explain the realm box there?
Yes.
The realm box, the GPTs of the realm, or what is that realm block for?
The realm. This is just the memory layout that we have on TFA. So the realm.
But the realm. Let me clarify my question. Realm memory is going to be come from the realm granules are going to come from normal world. It's going to be allocated, right? So
no, this is statically allocated. So TFA allocates memory to store.
So RMM. I can. The realm here refers to the main carve out reserved for just the RMM.
Just for the RMM.
Just for the RMM.
Okay. The name is particularly confusing. Although it says realm, it's referring to the fact that it's a realm physical address space, but it's only used by RMM. The realms themselves are dynamically launched, and you get a dynamically delegated page from non-secure. Yeah, I think you need some clarification over that.
Yeah, I'm writing this down to clarify it on the comments. Yeah, cool, thank you. So yeah, that's what I was meaning before. That realm, we store the RMM in that realm area, and then right before that we allocate a page of memory to be used as the shared area. Yeah, the boot manifest details. So currently, as mentioned before, the boot manifest for the current implementation of the boot manifest only has a version number. And we also cater for platform data, but we don't actually use that platform data, so we allocate that as a null pointer. Any platform must implement an API called plat_RMMD_load manifest. This API is in charge of allocating the memory for the platform data manifest and to populate that as necessary. It will also call some common code that will perform that will populate the common part of the boot manifest. The platform is responsible for defining any platform data manifest that might be needed to pass per platform data to RMM. Yep.
Are you gonna so when we can you go back to the memory map for a second? So
here.
Yeah, so I'd imagine the raw memory here, you're going to describe it in the manifest to the RMM as part of your RMM in it. So that region.
No, we don't describe this on the manifest. So the realm.
How does go ahead?
The realm area that you see here is actually where TFA loads RMM to run, and the shared area is actually passed on register X3 during boot up, and is where the manifest is stored. So then the manifest, we will store any other information that we need, but actually RMM doesn't need to know where it starts, and the shared area space is passed on register X3.
Well, the RMM's got to set up its own page tables, right? For like its code and data.
Yes.
So it needs to know. Yeah, it knows its load address. Does it know its size as well, the code size?
Yeah, RMM is able to obtain that information from its linker script. Is able to calculate well the different areas starts and then it creates the memory mappings.
I think this is the first version of the platform manifest. As you say, we need to describe the DDR ranges, basically different banks of DDR DDR ranges. And we have a follow-on task after this to define more fields to put in the platform manifest, basically to describe the memory range. But this is the first version. I think we'll be adding more and more stuff onto it. Yeah.
It sounds good. Thank you.
Yeah, that was actually that concludes the presentation. If anyone else have any more questions. Then over to you, Joanna.
Yes, thanks, Javier, Sobi. I've recorded the session. It'll be available in the normal place on trustedfirmware.org site. We have another tech forum next week. This one was an ad hoc one because we've had a bunch of subjects to describe or present. But thank you all for attending today, and hopefully see some of you next week. Thank you. Bye-bye.
Thank you. Bye.
Thank you. Bye.
Right. Thank you.